All right, so normal distributions are going to be a big part, well, they're going to be the major part of what we're studying in Chapter 5, and they look like a bell curve. They're symmetric, so this is your mean and your median, right? And they're described best by two numbers, the mean and the standard deviation. Standard deviation is, well, they're cut up into standard deviation sections. So if you go from here to here, which would be an inflection point in the curve from dropping down steeply to leveling out, that inflection point to your curve gives you what your standard deviation is. So two numbers can completely describe a normal distribution. So they're symmetric, single-peaked, and bell-shaped. This is the official way to report them, and this is the way that College Board wants you to. Again, they're described by your two numbers, the mean and the standard deviation, so they're reported normal, or if you have a little wiggle in front of it, approximately normal, with a mean at mu, whatever the number is, and a standard deviation of sigma. So the one previous would be capital N parentheses 80 comma 10. All right, so we're in Greek speak with this. We use the Greek letters because this particular mean and standard deviation are not numerical summaries of data. They're part of your model for the population. So they don't come from data. That's why we don't use X bar and S. So those numbers are called parameters. Parameters are for populations. All right. So summaries of data, on the other hand, like the sample mean and standard deviation, X bar and S, are written with regular letters. That's what we mean by Latin letters. And those are called statistics. So statistics come from samples, S to S, and parameters come from populations, P to P. Easy to remember. All right, so if we want proportions of observations for normal curves, we can use this little trick, and it's a great one. It's called your empirical rule. It applies to any normal model, and we can use it to get proportions. So this bulleted point, normal models give us an idea of how extreme a value is by telling us how likely it is to find one that far from the mean. We can find these numbers precisely. We will do that. But we're going to start out with your empirical rule, which is it's an estimate, but it's an extremely good one. It's only off by very, very small amounts. So, turns out that in any normal model, whether it's taller and skinny or short and wide, about 68% of your values fall within one standard deviation of the mean. 95% of the values fall within two standard deviations of the mean. And about 99.7, nearly all of them, fall within three standard deviations of the mean. And again, this works for any normal curve, and it makes a rule, which is the empirical rule, but it's also known as your 68, 95, 99.7 rule. So you need to memorize that. So there you go. 68 between plus or minus one standard deviation, 95% between plus or minus two standard deviations, and 99.7 plus or minus three standard deviations. So that leaves a very tiny amount in your tails beyond three standard deviations. What, 0.3%? Okay. Percentiles apply to normal curves too, and since you get scores from your SAT, PSAT, GRE, all those normal tests, you get a percentile rank for them just like anything else. Remember, the median is your 50th, Q1 is your 25th percentile, Q3 is your 75th percentile. Okay, normal curves show up in the natural world all the time. For us, we see them very frequently in our standardized normal tests like SAT, ACT, MCAT, all of those. Also, things like heights or skull diameters or the length of from your elbow to your wrist. All of those, if we get enough measurements from very random people, they will fall on a normal distribution. So they show up a lot in biology and the natural sciences. They're a good approximation for chance outcomes. You'll see that when we do probability, if you get a distribution for a probability model for the sum of the roll of two die, you're going to get something that looks pretty mound-shaped or bell-shaped. Many statistical procedures that we're going to do require a normal environment. But people want to put everything in a normal curve. Not every situation can be modeled by one. Incomes are always skewed to the right, so they don't fit a normal model. Don't force incomes into a normal model. All right, so we're going to do a worksheet on empirical rule, and the following are going to be some examples of what you're going to have to do with this. Okay, so here's a normal model for heights, and I guess for adult males. What is the likelihood that a randomly selected adult male would have a height of less than 69 inches? So likelihood is probability. So we're going to answer in proportions. All right. Well, 69 inches is at the median. So, or at your 50th percentile. So half below, half above. There you go, 0.5. What's the likelihood that a randomly selected adult male would have a height between 64 and 74 inches? Well, that's plus or minus 2 standard deviations from the mean. So according to the empirical rule, that's 95% of your observations. Okay, what is the likelihood that a randomly selected adult male would have a height of less than 66.5 inches? So that's from here down. Remember that this is asymptotic, so this is actually never going to end left or right. So 66.5 would be from here down, okay? That's going to be a little tricky. Here's one way to do it. If you go all the way from the right to the median here, that's 50%. This light green is 68%, so this piece here would be 0.34, right? Half of 68%. Did I say 66? I meant 68. So that would be 0.5 plus 0.34 is 0.84. Well, the whole thing has an area of 1, so 1 minus that 0.84 will give you 0.16. So that's one way to find it. Another way would be to go all the way from the left to 50% and then remove that 0.34, and that'll leave you with 0.16. So there's more than one way to do it. You just have to piece it together. All right, what is the likelihood that a randomly selected adult male would have a height greater than 74? All right, well, let's see. That's going to be 50% and up to the median, and then that's going to be up here, so that should be what, 0.84? Oh, it's greater than that. So let me redo that one. Whoops. Okay, 74 here is going to be, this would be 0.5, and this is half of 95, which is 0.475, and if you add those together and subtract from 1, you get 0.025. Oops, my bad. I misread the number. Try another one. All right, what's the probability that a randomly selected adult male would have a height between 64 and 76.5? Ooh, that'll be tough. All right. 64 to the median will be half of 95, which is 0.475. And then this would be 0.5, except you're going to subtract this little piece right here, which is 2.5%. So that would be, let's see here. Wow, they're doing it a little different. So let's see, again, my way would be 0.5, and then 0.5 minus 2.5 would be 0.475. So yeah, there it is. Huh. Let me double check that. I think I'll go ahead and pause here. I want to make sure that that's right. Just a second. All right, I'm back, and I was got my tail value wrong. All right, here's the way to look at it. So 0.64 to 0.69 is half of 0.95, and that's going to give you your 0.475. From 69 rather up to 76.5 is going to be half of 0.9975, which is approximately this number. This is a little rounded, so the two add up to this. So yeah, it gets a little tricky. It gets a little bit tricky. Yeah, so there will be some other examples that will be posted up online, and so this should give you a good start on your empirical rule, and yeah, let's just see how it goes. So thanks for watching.